Somewhere south of Hollister, California, there is a stretch of state highway where the asphalt is breaking itself apart in perfectly straight rows. Not from potholes, not from age, not from a single truck ever driving over it wrong. The cracks run in a strange staggered pattern, like a deck of cards someone fanned out sideways, and they have been doing this for decades. Nobody felt an earthquake the day those cracks formed. There was no shaking, no alert on anyone's phone, no news crew standing in front of a collapsed building. The ground just moved, quietly, the way it has moved almost every single day since long before that road was ever paved. This is the part of the San Andreas fault that nobody puts in the movies, a section that has been sliding past itself for longer than anyone alive has been watching, and has never once produced the kind of earthquake this channel usually tells you about. Last time, this channel corrected the biggest myth about the San Andreas, that it is one single crack waiting to unzip all at once. That correction is still true, but it left something out, something almost nobody outside a small community of geologists ever gets told. Part of the San Andreas is not locked at all. Part of it has never stopped moving. And the strange part, the part that should genuinely unsettle you, is that the moving part is not the dangerous part. The quiet, motionless, locked sections are the ones scientists are actually afraid of. Today we are going back to the most famous fault in America to look at the piece of it that behaves nothing like you were told, and to ask the honest question underneath all of it. If part of the ground beneath America has been slipping for 100 years without a disaster, what does that tell us about the part that hasn't moved at all? To understand why this matters, you need to picture the San Andreas not as a single line, but as three very different sections stitched together, each behaving in a completely different way. In the north, the section that tore loose in 1906 and leveled San Francisco is locked, stuck fast, storing up strain for the next time it lets go. In the south, past the desert town of Bombay Beach near the Salton Sea, the fault has not produced a great earthquake in longer than 3 centuries. Well beyond the interval scientists would expect, based on its own history. That section is also locked, also loading, also overdue in the driest, most literal sense of the word. But between those two locked, dangerous waiting sections sits something almost nobody hears about. A stretch running roughly 80 miles from the old mission town of San Juan Bautista down toward the tiny community of Parkfield, where the two sides of the fault are not stuck together at all. They are sliding past each other continuously, in tiny increments, day after day, year after year, without building up the kind of stress that produces a major earthquake. Geologists call this creep, and it is not a metaphor. It is a measured, monitored, physically real motion, tracked by instruments buried in the ground, at dozens of sites up and down that stretch of California, instruments that have been running since the 1960s. Here is what that creep actually looks like when it meets something built by people. Drive along the section of Highway 25 near the small town of Tres Pinos, not far from Hollister, and you will pass a stretch where the fault trace crosses directly under the road. The pavement there does not crack randomly. It cracks in that same staggered parallel pattern. Rows of short diagonal fractures called, en echelon, cracks. A signature so consistent that geology students are brought here specifically to see it. Every few years, the county repaves that stretch, and every few years, the ground quietly breaks it again. Nobody schedules that repaving around an earthquake. They schedule it around creep. Head a little further, and you reach San Juan Bautista itself, a mission town built in the 1790s, long before anyone in California knew a fault ran directly beneath it. The historic mission's old grandstand sits at the base of a slope that traces the fault line almost exactly. For more than 2 centuries, the ground under that town has been quietly shifting, and the structures that have survived there have survived not by resisting the fault, but by sitting on top of a section of it that never lets stress build high enough to snap. If you want a number instead of a story, here is one that geologists themselves treat as a landmark measurement. At a site called Melendi Ranch, close to San Juan Bautista, a single instrument called a creep meter has been recording the ground sliding at a rate of roughly 16.8 millimeters a year, a little over half an inch, every single year, without a single damaging earthquake attributed to that motion. Across the wider creeping section, the rate varies. Near the edges of that 80-mile stretch, motion slows to under 10 millimeters a year. Through the central 100 kilometers or so, It can run past 30 millimeters a year. All of that motion is part of a larger total. The Pacific and North American plates are sliding past each other along the whole San Andreas system at somewhere around 32 to 33 millimeters a year. And on the creeping section, a meaningful share of that total motion happens quietly, continuously, without ever loading up into the kind of stored energy that produces a great earthquake. And this is not some strange, isolated San Andreas quirk either. Head north into the East Bay, and you will find the Hayward Fault, part of the same tectonic family, running almost directly underneath one of the most famous college football stadiums in the country. The University of California's Memorial Stadium in Berkeley was built directly across the Hayward Fault trace back in 1923, before anyone fully understood what that meant. For decades, as the fault beneath it crept at somewhere around 3 to 6 millimeters a year, the two halves of that stadium slowly, silently pulled apart from each other. You can still see the evidence in old photographs: walkways that no longer line up, expansion joints that had to be widened again and again. Engineers did not fight the movement. In a major retrofit completed a little over a decade ago, they installed hundreds of base isolators, specifically so the two halves of the stadium could keep moving independently without cracking apart. That is the same family of ground motion as the cracks near Tres Pinos, just wearing a different disguise, sitting under 60,000 seats instead of a county highway. So, here is the rehook, because this is where the story turns and you need to hold on to it. If creep is constant, if it is happening literally today, right now, under a state highway and a mission town and a football stadium, why isn't this the dangerous part of the story? Why does this channel, and every seismologist who has ever studied this fault, treat the creeping section as the safe zone and the locked sections on either side of it as the real threat? That answer is the whole mechanism behind everything you are about to hear. And once you understand it, you will never look at an earthquake map the same way again. Earthquakes happen when two sides of a fault get stuck together by friction, and the rock around them keeps trying to move anyway. Nothing gives at first. The strain just builds, invisibly, for years or decades or centuries, stored like a bent piece of steel that has not yet snapped. Eventually, the friction loses. All that stored strain releases in a matter of seconds, and the ground lurches. That sudden lurch is what you feel as an earthquake. Creep is the opposite process entirely. On the creeping section of the San Andreas, the rock on either side of the fault is weaker, warmer in places, and riddled with certain clay-rich and talc-rich minerals that behave almost like a lubricant at the depths where the fault sits. This is the leading explanation among researchers, not a fully settled fact, but it is a well-supported one. Instead of locking together and building stress, the two sides slide past each other in tiny, continuous increments, the way a heavy door might slowly creak open under its own weight rather than being kicked in all at once. No stress builds because none is ever allowed to accumulate. The energy that would otherwise be stored for a future earthquake is instead spent immediately, every day, in amounts too small to ever feel. Every few years, that steady daily creep is punctuated by something in between the two extremes. A slightly faster slip event lasting hours or days, still far too gentle to feel as shaking, that shows up clearly on the creep meters as a small step rather than a smooth line. Researchers still do not fully agree on what triggers these episodic pulses, and that honest uncertainty is itself part of the story. Even inside the safest, best-behaved stretch of the most famous fault in America, there are still open questions nobody has answered. That is why the creeping section has never produced anything close to the great earthquakes that define this fault's reputation. The famous 1906 rupture tore along the locked northern section. The 1857 Fort Tejon earthquake, one of the largest in California's recorded history, tore along the locked section south of the creeping zone. In between them, across those 80 quiet miles, the historical record is almost embarrassingly uneventful. The fault just moves. This is also why Parkfield, sitting right at the southern edge of the creeping section, became one of the most heavily instrumented patches of ground on the entire planet. For decades, scientists set up an enormous experiment there, watching for a moderate, repeating earthquake that had struck that specific spot again and again through the historical record, hoping that watching it closely enough would teach them how to predict earthquakes more broadly. The earthquake scientists were waiting for did eventually arrive, years later than the original forecast window had suggested. A humbling result that quietly reshaped how the entire field talks about prediction. The lesson researchers took away was not that Parkfield failed. It was that even the most heavily watched, most thoroughly instrumented fault segment on the planet could still defy a specific timeline. That single result is one of the reasons every serious scientist today speaks in probabilities over 30-year windows instead of dates. And it is part of why this channel refuses to do fake countdowns as well. The instruments themselves have changed a great deal since Parkfield's early days. What began as physical creep meters, essentially long metal rods spanning the fault and wired to record any tiny shift between two anchor points, has been joined over the decades by a much larger invisible network. Continuous GPS stations, bolted into bedrock up and down the state, now track the ground's position to within a few millimeters day after day, and satellites using a radar technique called INSAR can compare images of the same stretch of ground taken months apart and detect the exact same creeping motion from orbit. None of this technology exists because scientists expect a disaster on the creeping section. It exists because the creeping section is one of the best natural laboratories on Earth for understanding how faults behave when they are not producing earthquakes at all, which turns out to be just as important for forecasting the dangerous sections as watching the dangerous sections directly. The decades of instruments left behind at Parkfield are part of the same wider network, roughly 40 creep meter stations strung along the San Andreas, Hayward, and Calaveras faults that still record this motion today, station by station, millimeter by millimeter, every single day. Here is the part almost nobody puts together, and it is the actual point of this entire video. The sections of the San Andreas that should worry you are not the ones that are moving. They are the ones that are not. Locked means loading. Locked means every year that passes without an earthquake is a year of stored strain added to a bill that has not yet come due. The northern section already paid part of that bill in 1906. The southern section, the stretch below the creeping zone, running down past the desert toward the Salton Sea, has not produced a great earthquake in more than 3 centuries. A silence that is not evidence of safety, but the opposite. It means that stretch of ground has been locked, loading, and building strain for longer than almost any other comparable segment of fault in the country. It helps to picture the whole system side by side, because the contrast is the entire point. On the creeping section, the ground itself is essentially confessing what it is doing in real time to anyone with an instrument sensitive enough to notice. There is no mystery to solve there, no hidden stress to estimate. Just a slow and honest slide that shows up the same way year after year on the same handful of creep meters. On the locked sections to the north and south, there is nothing to read at the surface at all. No cracked pavement, no offset curb, no sliding stadium. The rock is holding, silently, and the only way scientists can estimate how much strain has built underneath it is through decades of careful measurement of the surrounding land, historical earthquake catalogs, and models of how the crust is expected to behave under that kind of pressure. A moving fault leaves a paper trail. A locked fault does not. And that absence of evidence is exactly what makes the locked sections so much harder to reason about honestly. So, let's talk honestly about the odds, because this channel does not do fake countdowns, and it will not start now. According to the most recent statewide earthquake forecasting model used by the United States Geological Survey and the Southern California Earthquake Center, the chance of a magnitude 8 or larger earthquake occurring somewhere in California within the next 30 years sits at roughly 7%, up from an earlier estimate of about 4.5%. Once scientists began accounting for the possibility that ruptures could jump between connected faults rather than staying confined to just one. Within that broader forecast, the southern San Andreas, the locked stretch south of the creeping section, is identified as the single most likely fault in California to produce one of those very large earthquakes. Separately, for the San Francisco Bay region up north, a 2014 assessment by the Working Group on California Earthquake Probabilities put the chance of at least one magnitude 6.7 or larger earthquake striking somewhere in that region before 2043 at 72%, with the Hayward fault alone, the creeping fault under that football stadium, carrying the single highest share of that risk at 33%. None of these numbers describe a countdown. None of them tell you an earthquake is coming next week, or next year, or on any specific date at all. Scientists cannot predict earthquakes, not on the San Andreas, not on the Hayward, not anywhere. What these numbers describe is risk, distributed unevenly across a fault system where some sections are quietly bleeding off stress every day, and others have been holding their breath for lifetimes. So, 3 futures. In the most likely one, nothing changes for a very long time. The creeping section keeps creeping. The cracks near Tres Pinos keep reopening every few years. The stadium in Berkeley keeps flexing gently against its isolators, and the locked sections on either side keep loading in complete silence, exactly as they have for the entirety of recorded California history. Most years, on this section of ground, absolutely nothing newsworthy happens, and that is not this channel failing to find you a story. That is the honest baseline. In a more eventful future, one of the locked sections, most likely the long, overdue stretch near the southern end below the creeping zone, produces a major earthquake sometime within the coming decades, consistent with what the probability studies already describe, causing serious damage across a region that has had generations to prepare for exactly this outcome, and, thanks to that preparation, would very likely survive it with better resilience than 1906 or 1857 ever had available. And in the genuine worst case, the kind of multi-fault rupture that pushed the statewide magnitude 8 probability upward in the first place, a rupture on one locked section triggers a chain reaction into a neighboring fault, producing an earthquake larger and more complex than any single segment could generate alone. Scientists consider this possible. They do not consider it likely in any given year, and there is no data suggesting the quiet creeping section in the middle would somehow trigger such a chain. If anything, it may act more like a buffer than a bridge. None of these 3 futures depend on the creeping section suddenly changing its behavior. Nothing in the historical or modern instrument records suggests the stretch between San Juan Bautista and Parkfield is about to lock up, and nothing suggests a rupture on a neighboring locked section would somehow travel straight through 80 miles of ground that has spent a century proving it releases stress rather than storing it. If anything, the creeping section is one of the more stable, well-understood variables in an otherwise uncertain system, which is precisely why it makes such a poor villain for this story and such a useful contrast for the sections that actually deserve your attention. Here is my honest opinion, after everything the research shows. I think most people who fear the San Andreas fault are afraid of the wrong part of it. They picture one long crack, silent and sinister, waiting to open beneath an entire state at once. The real picture is stranger, and, in its own way, more reassuring in the middle, and more sobering at the edges. 80 miles of that fault have been moving almost every single day for as long as instruments have existed to measure it, and that section has never produced the disaster this channel usually covers. It is the silence on either side of it, not the motion, that should hold your attention. A fault that creeps is a fault that is honest about what it is doing. A fault that has gone quiet for 3 centuries is a fault that is keeping something. I want to ask you something, and I would genuinely like to know the answer in the comments below. Have you ever driven through California, maybe on a family trip, maybe decades ago, and crossed a stretch of road without ever knowing you were passing directly over one of the most studied cracks in the Earth's crust? Or do you remember a much older memory? A grandparent, a parent, someone from an older generation telling you as a child that California was going to fall into the ocean one day. I heard that same claim more than once growing up, stated as flatly as a weather report, and it turns out to be one of the most persistent pieces of folk geology in American life, despite having no real basis in how plate boundaries actually work. Tell me which one is true for you, the quiet crossing you never noticed, or the childhood warning that turned out to be exaggerated. I read every one of these. If this changed how you picture the ground under California, the honest way to tell me is a like on this video. It genuinely helps this channel reach more people who are curious about the same questions you are. And if you want to keep tracking the ground beneath America with me, subscribe, because the next investigation on this channel heads north, out of California entirely, to a stretch of coastline where the danger is not a crack you can point to on a map at all. It is a fault hiding completely offshore, its entire violent history recorded not in old newspapers or damaged buildings, but in the rings of trees that drowned standing upright, and in tsunami records written down on the other side of the Pacific Ocean by people who had no idea what had caused the wave that reached their shore. That story is coming next, The ground beneath America is speaking. Make sure you are listening.